Hi, everyone. Welcome to what I hope will be the first of many meetings for a Rust of Formal Methods interest group. I'm happy to have you all here. And the purpose of this first inaugural meeting is partially to introduce the group. Of course, we'll have a talk by Vytautas Astraukas, who works on Prusty, on how they leverage Rust typing to help formal verification of Rust code. But first, I'd like to talk to you a little bit about what I'm hoping this group will become, and looking for your feedback and participation. So, sorry, 1 second. There we go. So first, if you haven't seen this before, we just have some basic Zoom etiquette. During presentations, please keep yourself muted, keep your camera off. When we get to question and answer sections, turn on your camera, and Ernest will be going around to make sure that you each get a turn to ask your question. And if you'd like to ask follow-up questions, leave your camera on so that we know that you're interested. And if you don't have a camera or you would rather not use your camera, use a hand raise reaction in Zoom so that we know that you would like to speak. All right. So who are we? For the moment, it's I'm Xavier Dennis. I'm helping to organize this event. We also have Bas Spitters co-chairing, and Ernest Kissiedu, who's facilitating our conversations and helping us a lot with the logistics and all the Zoom stuff, and a lot of very fun but challenging issues. What is the Rust Formal Methods interest group? The idea is to help gather together all the different people and different teams that are working on different formal methods tooling in Rust, the people who are interested by the potential of formally verifying the Rust code, and people from the Rust compiler teams, and try to put everybody in the same room so that we can discuss our shared problems, collaborate on various solutions, and generally just avoid working each in our own corners. So the idea is really to build an open and as inclusive as possible community. So going from academic researchers like myself to industrial users who might be trying to actually verify Rust code. And as well, I'd very much like to be able to include hobbyists, so people who don't necessarily have the academic background or an actual concrete use case, but who are still interested by these questions. And I think their insight will also be very important into helping make these tools a little bit more mainstream. And as I said, we really want to encourage collaboration between different groups and make sure that everybody's good ideas don't stay in their corner, but instead gather some wider adoption. And another key thing would be to help gather feedback from formal tool developers, so that we can help improve the APIs in Rust, because most of the Rust formal verification tools will integrate with the Rust API, and it's not a use case that was originally thought of for Rust. And so I know I've encountered some of these weak spots myself. And so if we can get together and figure out what we need, it makes it, I think, a lot easier to present this as change proposals for the Rust compiler. And finally, of course, I'm expecting the participants of this interest group to be respectful of the Rust Code of Conduct, the Rust Community Code of Conduct, which we'll go over in a little bit. And I hope that's not too controversial. And on the other hand, what we aren't is also as important. So the first thing is that this interest group is not aiming to be a standards body. We don't have official authority within the Rust project. And I don't think we're even at that point where we can start envisaging any sort of standardized Rust formal methods tooling or anything like that. So not here to decide on the one true way of building a Rust formal verification tool, or on the one true way of verifying Rust programs, or the one true specification language for Rust programs, all these kinds of things. We're really here, again, to encourage collaboration, to encourage discussions, to figure out what points people agree on, what points people disagree on, what the different options are. And then as well, we're not a platform for commercial promotion. So this is really a group that is meant to focus on the theoretical and engineering challenges of building formal tools. It's not a place for unrelated discussions or promotion of other enterprises. There are plenty of other spaces to discuss this within the Rust ecosystem, and it would be good to keep this this forum focused on its purpose of making Rust formal tooling and formal methods more tractable, more widespread, and more enjoyable to use for everyone. So you may be wondering how you can actually help the RFMIG. The first thing is, of course, that we will be organizing monthly meetings. Each meeting will have a sort of prearranged topic or theme, and an invited speaker who will give a presentation related to this to that month's theme. So we will be having a meeting in October, and I will announce the date shortly. As well, we have a repository on GitHub, a coordination repository where you are invited to open issues if you have any questions, organizational, logistic, or anything really. It just gives us a nice centralized forum on which we can actually track people's suggestions. Of course, we also have a website. You can also find the GitHub repository for the website if you would like to contribute to any of the pages or anything like that. Then we have our Zulip channel on the Rustlang Zulip. So I actually think, sorry, it should be a WG, not a T there. So the Zulip channel is WG-formal-methods on the Rustlang Zulip. Of course, hop in there. Plenty of good discussions, and I hope there will be more after this meeting. Then also on Zulip, I had this idea of a little challenge or exercises that people could do. So the idea is that there's a few simple Rust programs in a Zulip thread, and if you'd like to participate, just specify what you think those Rust programs should do using whatever syntax or specification language you would like. And the idea is that then in October, we'll discuss the different entries and sort of go over how people naturally feel like they would naturally specify these Rust programs. In the interest of stimulating discussion on how different tools view the verification of different Rust programs. Right. So the code of conduct. We follow the Rust code of conduct, which can be found on the Rustlang website. I should probably have linked it here, but I encourage you to Google it if you're unfamiliar with it. But in short, please exercise your consideration and be respectful of others in your speech and actions. Attempt to collaborate and be non-conflictual if you can. And please restrict yourself from demeaning, discriminatory, or harassing behaviors and speech. Those will not be tolerated. If you harass people in this call, you will be kicked from the call. And if you feel like somebody has been harassing you or being discriminatory towards you, please contact either me, Ernest, or Bas, and we'll take action as appropriate. Then, of course, be mindful of your surroundings and your participants. And as it says, if you feel like there's a dangerous or a problematic situation, please notify one of us so that we can take action if needed. All right. So thanks for listening to my little spiel. I hope you'll enjoy the talk. I put the various places, various forms of communication for this interest group up here. We also have a Twitter account, where I'll be broadcasting various news related to the interest group. And then we have today's agenda, where Vytautas Astrokas, who works on the Prusty verifier for Rust, will be talking about Rusty verification, how they leverage the Rust type system to help simplify the challenges of verification. All right, and I guess I'll hand over the mic.
Thank you. Okay, so let me try sharing. Okay, so I hope you see my screen. So hello everyone, I'm Vytautas, and or simply speaking, V. I'm a PhD student at ETH, and as Xavier already mentioned, I'm working on a verifier for Rust called Prusty, and in my presentation today, I will try to explain why I'm so excited about working on Rust verification. So let's start with a, this is not working, with a simple example. So let's imagine that you wrote some tricky and important piece of code, for example, binary search, and you want to convince yourself that your code is correct. A typical way of doing this is by writing some unit tests. For example, a regular test function with where you call the binary search function with various arguments, and you check that it produces a correct result. However, if you apply this technique, you are unlikely to discover bugs or things that you have not thought about. An alternative approach would be to use random testing, for example, by using the prop test library, which with this way you can essentially just generate a bunch of random inputs and then compare them with some trivially correct or obviously correct solutions, something like linear search, for example, to make sure that your binary search is matching the linear search. This, however, random search has a limitation that it is unlikely to find inputs or examples that trigger bugs, but are extremely rare. For example, this function fails with only a single value, and random testing is quite unlikely to hit to generate this value. Typically, most developers stop here at this by using manual or random testing. And in my opinion, that shouldn't be the case. And I think at least some of you will agree with me that we should find ways how to give more other tools for developers to ensure that their code is correct. So one of the Alistair, who not sure if is today in the meeting, but was definitely around, recently published a paper where we tried to actually approach this. And the idea was to reuse the prop test interface to allow using symbolic execution engine and model checking and other methods for basically testing user code. And the key advantage of, for example, symbolic execution is that it tries deliberately to find inputs which lead to previously untested behavior. And in this way, it is way more likely to find bugs that are triggered only by a very small number of examples, like triggered only by rare examples. So this is great. What I'm doing and we are doing in our Prusty team, we are exploring, we are working on deductive verification, which I'll explain in a minute. And we are basically trying to do, we try to reach the same goal, trying to find how we can simplify deductive verification that it is approachable for larger masses of developers. And in the rest of my talk, I'll try to explain what we have learned while pursuing this goal. So what exactly we are trying to achieve and what is deductive verification? So imagine that we want to build a magic box that to which we feed in the binary search function, which you saw before, plus specification. For example, for binary search function, it would be that assuming the input slice is sorted, we want to ensure that the function always returns index of the element if and only if that element is in the input slice. And this magic box either says that your program has a bug and preferably gives a counterexample, or generates a proof that this is in this specific this function definitely satisfies this specification with all possible inputs. So not just some things we tested, but really all possible inputs. Okay, so before we go further, to explain how we like how such magic box could be built, I would like to explore what to explore the experience from our programming languages, because Rust is comparatively new, and we have a lot of experience from our programming languages. Here I have 4 languages that each indicates some group of programming languages, and I would like to start with the most academic, Haskell, which is a pure functional programming language. As some of you probably already heard, for Haskell, there is a verifier called Liquid Haskell. And I would like to walk you through a simple example of max function. So this function takes 2 arguments, x and y, and it returns the non-smaller of them. Formally, we could specify this function as that the result value, which is denoted by r, is one of the 2 arguments, and that it is definitely not smaller than both of the arguments. In Liquid Haskell, we could directly translate this as this condition. It's basically a Boolean expression. And as you can see, Liquid Haskell has 2 very nice properties. The specification is expressed in regular Haskell, so there is no additional things for the developers to learn. We can just write specification with the knowledge that we have about the language. And another nice property is that the specification is automatically checked. So that's what we have for pure functional programming languages. Now let's look into what situation is for another like more mainstream programming languages such as Java, which also pays quite a bit of attention to correctness. So here we have function foo that takes 2 counter objects, x and y. It increments the counter y, and we want to assert that the value of counter x didn't change. And yeah, basically the main question is this guaranteed to pass? And many of you probably already know that if we pass the same counter, we create counter z, and we pass it as both arguments, then this assertion will fail. One way of prevent that would be to add a precondition which requires the counters to be different. So this works in this case, but would it work generally? Let's have a look into a slightly more complicated example that instead of counters takes trees. So from this signature, I would expect that the function receives 2 trees that are like regular trees. However, in Java type system, there is nothing that would prevent caller to pass basically a graph which obviously, if I'm modifying now one of the trees, it would definitely affect the other one. So we have a problem. We could try to again write a precondition that forbids this. However, this precondition has several problems. One is that we most likely will have to use a complex logic. Most common choice nowadays seems to be separation logic, which is something that, basically something that most developers haven't never seen of, and would require a lot of training for them to master, and they're likely to be a roadblock for adoption. Another thing is that even the specification I wrote here, it says about the shape of the values that we pass in, but it says nothing about actual functional specification of like what does this code supposed to do. In other words, to verify programs in Java, we need to write, even with the current state of the art, we would need to write a lot of boilerplate code just to get the tooling working before we can actually do any proofs. It turns out that the same problem is actually is common for all mainstream programming languages. So it's the same for Java, C#, C, C++, Python, and so on. So we have these two groups. One, the aliasing is not a problem, so Haskell pure functional languages, and one group of mainstream programming languages, the aliasing is a real roadblock for verification. And obviously, the question here is to which group Rust belongs. So let's look into the an example like this Java example with trees translated into Rust. So here we have X and Y passed as trees, and since X and Y are owned, we actually know that we are disjoint, that we are different. And from the transitivity of ownership, obviously we're assuming here no internal mutability, we get also that these two trees are disjoint, that we are separate. And this gives allows me to speculate that we could, with Rust, we could expect to have tooling that doesn't require these using these complex logics for writing specifications. And based on what I just showed you, so Haskell approach and logic approach, we actually have two ways how we can go about building verifiers, deductive verifiers for us. So one is purification that Xavier is exploring with his tool Crusoe. So I'm highly oversimplifying here, but basically the idea would be that the black box would take the Rust program, convert it into equivalent functional program, attach the specification, and feed into verification infrastructure designed for verifying functional programming languages. Our way is more coming from the Java and other mainstream programming languages world. Here we have tool Prusty, where we take a Rust program, we extract the type information, we use the type information to generate separation logic assertions in this complex logic without showing any interaction with the user, just generating under the hood and feeding the generated proof into the verification infrastructure designed for reasoning about heap manipulating programs, in this case, Viper. So here we have two approaches inspired by two different ways of thinking. Both of them have their advantages and disadvantages. yeah, if you are interested in that, I'm up to talking about later. So now I would like to show you a demo how actually Prousty works. Let me so hopefully you see VS Code. This is Visual Studio Code having with Prousty plugin. You can see hopefully the font is large enough that verification succeeded. So what I have here is the foo function whose signature are shown you before. And yeah, basically like with counters example, I'm modifying y and checking that the size of x didn't change. And since we are in Rust, if my hypothesis holds, we expect that this assertion actually passes without much of annotations. And as you can see, Prousty claims that yes, indeed, verification succeeded. And the only specification that is not commented out is pure on function size, which tells the verifier that the size function is deterministic. That means its result depends only on its argument. So, for example, it doesn't generate random numbers under the hood. So that is the only annotation that I need in order to verify this assertion. Obviously, if we are trying to verify things, we are interested in something more complex. Like, for example, I would also like to know that how the size of 3y changed. So, for example, would like to assert that size of y increased by 1 because I inserted an element into the tree, so expect that the size increased by 1. Yeah, that's so for that to work, I need to. So as you can see, currently it doesn't verify. The reason for that is that we are doing modular verification. So we are checking each function model separately, and therefore this Prousty doesn't know what the method insert does. Therefore, we need to tell it, and we can do that by writing a post condition that is just saying what this method ensures. And we, in this case, method insert ensures that the new size after this method is called is equal to the old size, that is what was before the method was called, increased by 1. Prousty is complaining that post condition might not hold, and the reason for that is that I have another function called method call in here that of a constructor, and obviously I need to tell Prousty that the newly constructed size of a newly constructed tree is 1, and now the verification succeeds. As you can see, all specification so far is mostly Rust expressions, Rust potentially recursive function, and alt modifier that allows me to talk about pre-state for mutable references. Like recursive data structures like trees are nice in a sense that I can actually express even more complicated properties in the same way. For example, I can also, just by using recursive functions, express that sortedness, that this is actually binary search tree, which would, and then require that, for example, assert that y is sorted For that, I obviously need to require that y is sorted at the beginning, and I need to make show that that insert method maintains sortedness, and obviously tell that newly created tree is also sorted. And yeah, now it should. The arrow here is in the wrong place because I added code and it has a error message on the line. So now it should verify. Since I'm using Zoom, which consumes a lot of CPU power, verification runs much slower, and probably also concurrent jobs. Yeah, so while it's running, let me continue. So that's basically the nice property about recursive data structures, that we can, it's still, yeah, yeah, let me continue. It's likely that simply the verifier is actually timing out with Zoom running in the background. Yeah, so the nice property about of binary search tree of recursive data structures is that we can write properties by simple recursive functions. However, unfortunately for us who want to verify things, is that programmers tend to not use that many recursive data structures. They more prefer arrays, vectors, and similar things because we are much faster. So here I have another example, the binary search, which I showed at the beginning. Let me zoom out that you can entire function fits into the screen. So it is this code I copied from, I took from Rosetta, and yeah, the specification is basically what we wrote before in Word. So we take we require that the input array is sorted, and result is either index of an element that is equal to the one we searched, or we ensure that if we return none, that means there is no such element in the input slice. The thing that comes with using arrays, slices, vectors, and so on is that we are typically forced to use quantifiers. And that's an additional challenge for users. However, as you can see, still in this program, I'm staying within first order logic, with which hopefully most developers are familiar from the bachelor studies, if they had discrete mathematics or subjects like that. As you can see, Proust is complaining here, and this example is illustrates why for code that is commonly used and tricky to write, so like algorithms like binary search, is deductive verification is really useful. So this code is, as I mentioned, copied from Rosetta, and it has a bug on this line. That the problem is that we are like missing when going down. In some cases, we will miss the last element of a vector. And if, for example, the element we are searching for is the last one, the program erroneously will report that it's not in the range, while it is actually there. And that's because of a division here that drops the last element. A typical way of fixing that is by using low and high range. So basically changing all the code to use low plus high divided by 2. However, if you wrote code like this, you basically have you introduced overflow at this point. And if you are on 32-bit system, that actually this overflow can actually cause issues. The correct solution would be to have the size divided by 2, and then midpoint would be base plus half, and to make sure that we don't cut off the last bit to actually subtract from size with half. And now hopefully the SMT doesn't cause problems this time. Yes, so in this case, Proust agrees with me that this program is correct. Okay, let's me go back to slides. Yeah, so what I've shown you is a tool that is without exposing complex logic to the users, it allows us to verify the correctness of the programs. And the question is, are we completely done? Can we just go enjoy life, or is there still things to do? And what I show you actually is just a small fragment of currently Prusty and our tools support only a subset of Rust. And since Rust is a huge language, we are still plenty of work for us to figure out how to implement support, for example, for traits, closures, higher order functions, iterators, async, and many other things. And not only figure out how to support them in general, but also how to support them in such a way that developers without doing PhD and formal methods can actually use these tools. So in other words, there is still plenty of work for many PhD students to work out and for things to implement. And obviously there is also always unsafe code that can hit us at some unexpectedly and cause problems, and we need to figure out about that. So with this, I would like to end my presentation, and yeah, if you have any questions, free to ask.
All right. Thank you very much for this great presentation and overview of Prusty. It was very interesting. So I think, yeah, at this point, yeah, like Ralph said, impressive demo. Of course, we'll always have the little like demo bugs, right? SMT decides his timeout at just that moment, but that's part of the game. So as we said, if you'd like to ask a question, just turn on your camera or use the hand raise, and we'll give you some time to speak. So I'll give everybody a few seconds to decide if they have any questions to ask.
So it looks like my video is not working.
It is, Bas. It's working. We can see you. We can hear you.
Okay, that's very good.
So what we'll do is there's a few people who have switched on their cameras and started, so we'll go in a specific order of camera order first. We'll start with Daniel. If you wanted to ask your question to Vitutas, please unmute yourself.
Yeah, that was a great talk. So I'm curious about the specification language and sort of how much power you think that needs and how hard it would be to unify across different tools. Particularly, so I'm interested, we want to have specification for RMC, and it would be great to sort of merge that with yours. And one thing in particular we've been thinking about is this idea of having sort of object invariance or data structure invariance, where often we think the specification is going to be at the level of, all of the operations that work on this API maintain this invariant when the object, between calls on the object. Is that something that you've thought about?
So just to answer about object invariance and type invariance. So as you saw, this sorted function is probably something that normally I would put into the type invariant because it's the invariant of a binary search tree. So that's, and yes, definitely we want to have support for invariants, and we actually used to have them in Prusty before we did compiler upgrade and we broke that feature. So, but we are planning to reintroduce it at some point once we figure out the parsing and other small things. But yeah, that's type invariance is definitely something we want to have. And I think that is required in many examples. Talking about the specification language itself, is that I would like to see how far we can get with staying with a simple logic as possible. So with as simple connectives and most intuitive elements. Obviously, if you, for example, jump into unsafe code, there will be we will definitely require much more complex machinery. But yeah, for safe code, I would prefer would love to find ways how we can use a simple preferably something like Rust annotation, Rust Boolean expressions plus some very minor thing on top.
Cool. Thanks.
Great. Thank you very much for that, Daniel. We'll then go to Nico. Hi, Nico. And then I saw Pointer Bender raised their hand. So we'll go to Nico and then Pointer Bender if they still have a point or a question for Vitutas.
Okay, sounds good. I have kind of 3 questions, I think. And you can pick your favorite. I guess the first one was that I was just curious to hear a bit more about how you integrated with Rust-C and so forth. And I'm always interested to talk more about that side of things. But the second one is maybe a narrower point. In your example on the binary search, there were a number of things in there that seemed, I'm trying to remember the exact example, that seemed more like entry invariance or even deducible from the surrounding code. I can't remember now. There was one specific one. It was the while loop said sort of while size greater than 0, and then you have body invariant size greater than 0. Is that I'm not really familiar with the state of the art of verification and so on, but that seems a little repetitive. Have you looked into, or anyone on the call really, I think a key thing for making all of this really work for people is going to be reducing the amount of why can't the compiler figure that out for itself as much as we can. Definitely noticed that when the Rust compiler type rules are very simplistic, people aren't impressed by how elegantly simple the type checker is. They're just annoyed. But so that was question number 2. And question number 3, you mentioned prop test early on, and I couldn't quite tell what happened to that direction. I thought that was sort of interesting, this idea of, I'm interested in this continuum, whether it be through prop test or elsewhere, of runtime checking into static checking. right? And things like body invariant, you could imagine they begin as assertions and get dynamically checked. Have you sort of played with that at all? Those are my 3 questions.
Okay, so yeah, let's start in a row. Then integration with RC, we are using the typical RC driver approach. So basically, we override the driver, we run up to the type checking, then we get this after analysis callback, and then we basically get typing context and try to get the information we need from the compiler. So one thing that you should remember is we are getting Polonius information in this a special way to get the actual borrow checker information. So that's, for example, one of the differences between Crusoe and Prusty is that Crusoe doesn't need this borrow checking information because by doing purification, it's just turns out to be not necessary. For us, for Prusty, if you want to generate separation logic proof, like borrow checker information, precise information is necessary, because like lifetimes and things like that, basically I view them as a proof annotations that developer does, and then Rust compiler does the proof that code is memory safe, and then we kind of do the same proof in separation logic. Yeah, so that's kind of more or less integration. If and kind of the maybe most important point for many of the who are developing tools is that like important point to know about aliasing information in Rust compiler is that most people probably are aware of that there are multiple MAR. So there is this MAR on which borrow check is running, and MAR that is actually then optimized and saved, for example, in library files, and also from which code is generated. And Prusty, as far as I know, is currently the only tool except the new slicer that recently appeared that is running on the borrow checker MAR. So that's one of the kind of pain points, as I see, to actually for integration with a compiler. But I guess we can talk about that point in detail once the time comes in these meetings. Now, answering your second question about, if I understand you had in mind this like invariant. Yes, so this is kind of, I would say, a bug, and so it would definitely should be inferred in this case. It just kind of one thing, like there is a technical reason why we need this invariant, but yeah, I hope to fix this. In general, for things like this, there is like we could reduce the amount of annotations needed by using inference, for example, based on abstract interpretation, and that would be I'm pretty sure that abstract interpretation for us would perform much better than for Java and other languages. And yeah, so kind of these things should be possible to infer. So there is still quite a bit of things we can do to reduce this overhead. Just that's something we haven't done yet. But I think it, like if someone try to do that, I think it would be really, really interesting and beneficial, especially if someone figure out how to do that on compiler side on MAR, and then expose it so that all consumers could use it. Because I mean, this information is, I think, really useful for compiler for doing optimizations. For example, here we have array access, which is involves a bounce check. But if basically this invariant implies that the check is not necessary, so the compiler could optimize the check out, and probably LLVM already does that. But doing it on Rust level would be, in my opinion, would be more precise. Would have all the benefits of doing optimizations on the Rust C side, and plus the compiler consumers could use it. Talking about runtime checking and versus static verification, I think it's a huge top. So I'm not expert on that. I think it's really interesting thing to explore and try. So Alastair tried a bit, like went into that direction. In our group, we also had the thesis from Maria Christakis, who tried to actually bridge this gap between testing and verification. So just to give for others who may not be that familiar with range, is that if you do like if you have a concolic testing tool like CLI, and you have a code that, for example, doesn't have loops or recursion, you actually can use that tool for verification, because it can explore all possible interesting paths and actually know that it did that. And in that case, that would be equivalent to verifying code. So that also is an interesting direction to explore. But yeah, currently we haven't done that. And yeah, if we also would be super interesting to talk about that at some meeting.
Thank you.
Great. Thank you very much. We're coming up to time. We've got 5 minutes left. So if anyone has any points or questions before we hand back to Xavier for the closing address, please share them now. Pointer Bender, sorry, you were next to ask a question if you still have it, or if it hasn't been answered by a previous question. Yeah, please go ahead.
Oh, great, thank you. Well, first of all, thanks for the presentation. This is really interesting stuff. I didn't know this was already possible today, so I'll be definitely giving that a spin. I'm an end user of, or potential end user, I should say. I still have to try it out. And I was wondering, how does this work with debug functions in Rust? I think I know the answer from the previous answer. It's probably what the Rust compiler feeds into your program would get processed. So if you build it in release mode, it would be different as when you build it in debug mode. Oh, can you guys hear me, by the way?
Your audio is breaking a bit, but did I get correctly that your question is what happens with debug assertions?
Yeah, that's correct.
Yeah.
Thank you.
Yeah. So yes, with debug assertions basically depends what compiler does with them. But the point is that since we are compiling under, like Proust is acting as a compiler, during verification, we actually just force the compiler to always have debug assertions enabled. So that's why we are always present and always checked. Yeah, so that's basically during verification, they would be equivalent to real assert statements.
Great. Any follow-up points? Okay. Yeah, Xavier wants to come in, and Yusuke, I saw you switch on your camera. So if you would like to make a point, we'll come to Xavier, and then we'll allow you to come in after, if that's okay. Thank you very much. Xavier.
Yeah. So I just had a quick question. During your presentation, you mentioned the difference in the approaches that we're taking in Clouseau and that you're taking in Prusty. Have you given any thought to whether those two could be combined somehow? Like, would it be possible? Do you think it might be possible to, use both approaches simultaneously and somehow in a way where the results are still compatible and sound? Or is that not interesting, or just too unthought or like unresearched?
I think so. Basically, the difference between the two approaches is that one of them trusts the Rust compiler and system. So basically, when you do purification, you kind of assume that the Rust compiler is sound and so on. In our case, at the moment, we are still have points where we are assuming that, but at least in general, what we could do, we could basically throw away the Rust compiler from the trusted code base and just say, okay, we have this proof that is complete, that proves everything. And yeah, and kind of you have various points of how these things can be combined. So for example, I expect that Clouseau will be faster simply because the proof is simpler. Because we are doing the separation logic proof, which is I actually forgot to show the encoding, but for the binary search example, the generated thing is over 1,000 lines. So it's basically blows up more than 15x, I think. So that's kind of complex thing, which gets then pushed down to the verification infrastructure and is potentially causing quite a bit of slowdowns. But on the other hand, we have this advantage that we could not trust compiler. So here you can have various options, like for example, using purification approach during development, when you trust at the beginning the compiler to get quick feedback loop, and then, for example, for nightly builds, when you want to have, I don't know, certified thing, you just push it down to use another approach. And assuming both verification tools are sound, there should be no observable differences. It's kind of one approach,
Yeah.
and there is quite a bit of various variations. I think how you could combine and how it could play with that.
Yeah, thank you.
Great. Yusuke, please, if you'd like to come in.
Yeah, so thank you for the great talk and demo. So I have a question about support of unsafe code. So because Prusty does verification using separation logic and Viper, and also Viper is quite successful in verifying many interesting pointer manipulating programs, and I wonder how Prusty can verify how far Prusty can verify interesting unsafe programs. So what do you think about that?
So currently, if you try to run basically any unsafe code on Prusty, it will simply we have an it will say not supported. If we just because we want to give sound guarantees. Now the thing is, if you it really depends of what kind of unsafe you have, because Rust, the interesting part about unsafe is that you have more this the proof of unsafe code. To prove that unsafe code is correct, you actually not just need to prove that it's like some specific function is correct, but you actually need to prove that like a safe function that wraps on safe code is valid with all possible inputs. Like basically, no matter what crazy stuff the safe client is doing, your own safe code must survive that. And that's something which we are trying to figure out how to actually write down. So Ralph probably is more of an expert here to talk about that, how to like, because that was basically the point of Rust Belt. And like in Proust, we have all the, we do have like separation logic with which we can try going for that direction, but we are definitely not there. We're still quite like, especially because compared to like Rust Belt, we are aiming for automation, and that's where basically things get really hard. Because in safe, like even if you have if you have a safe code with pointer manipulation, one way of doing that, going into unsafe, would be to just pull out all full separation logic. But that's question is that user friendly enough for developers? So there's a lot of questions like to figure out, to basically to pursue this goal of making verification approachable.
Thank you. So I think like supporting safe Rust plus only cell type or mutex type with some axiomatized API can maybe amenable to Viper.
So if you so since verification is modular, if you have safe abstraction and you just want to trust it, that's just works. I think it would also just work for our, like for Crusoe. It's just you have because we are verifying each function separately. So if you have something which we cannot model and we cannot verify yet, but you have an interface which is expressible in Prousty, that's not a problem. It would just work. So that's, for example, how we dealt with vectors at the beginning when we still didn't have like proper support for them and so on. So like you simply have a like put a wrapper type which you trust, and yeah.
Thank you. So yeah, I kind of wondered that if like if Viper, I wondered if Viper can work better than a mere purification approach for some more imperative reasoning. Like
So one thing there, it's so for the point is that Rust is interesting, and the examples where we need to like they actually separation logic would seem to be better compared to purification. For these ones, we still like in this unsafe code guidelines group, when they like every time I check it, there's like still a bunch of open questions how to actually deal with that. So there's like a bit of also open semantics and things like that. So so simply speaking, this is quite a large topic to discuss, and yeah, I would maybe propose to have it like even as a separate thing, or to discuss like this specifically unsafe code and language semantics, because many things with one of the problems for verifying safe code is that a lot of things are simply still not decided, like what are aliasing guarantees in some cases, what is allowed, what is not allowed. And that's kind of when you want to verify, you actually have to know this.
Okay, yeah, thank you for sharing your idea. Thank you so much.
Great, and thank you all for the questions. Thank you all for sharing. I'm now going to hand back to Xavier for, well, first I think we'll, is Bas in the room still? Bas, are you here?
I'm here, yes.
Great, we'll allow Bas as co-chair to say a few words, just to round us off. And then we'll hand back to Xavier to give us a closing address and to set us for the next event coming up, the next one of these meetings coming up. So Bas, if you'd like to just say a few words. Thank you.
Just want to say that it was a great talk and I really enjoyed it. And I really enjoyed the discussion around it and the all the activity on both on Zulip, but also the discussion in the chat. And I mean, we already had some exciting discussions about building a joint language and a joint tool where, I mean, about building something like pharmacy as Xavier suggested. So I think there's a lot of possibilities for collaboration. And finally, I want to thank Xavier for all the work he put in putting this together. So having said that, I just want to give the word back to Xavier.
Yes.
Thank you, Bas, and thank you, Ernest, as well, for all your help managing the meeting. So I hope you all enjoyed our first session, and I hope that, like me, you see the potential for Rust and for formal methods in Rust in particular. I really think that, like Vytautas suggested through his talk, the Rust type system allows verification in a very different way from traditional imperative languages. And I think it has a lot of potential, and I think that we can build some really great tools that will have some actual usage and impact in the world. At least that's my secret hope. As for following meetings, I would like to organize a meeting next month with a sort of broad theme of specifications and specification languages. Please go look at the specification challenge thread on Zulip and write some suggestions. The whole idea is that you can sort of make up what you think a specification language for Rust would look like, and just write what you feel like is a natural way to specify these programs, and add programs if you'd like to. So as I said, next month, we'll have a talk on the subject of specifications, or broadly related to, and then a discussion, and I'd also like to have a discussion of the specification challenge. I'm currently thinking of next month, so in 4 weeks, on October 18th, another Monday at the same time. I'll set up an invite soon and get that out officially. And then I'll write up the proposed calendar I have until at least until December for sort of the subjects of upcoming meetings, so that people can sort of plan out their time and try to, you don't have to come to every meeting that way, at least you can jump in on the ones that you think might be relevant to your particular interests. Though I would love to have you all with me every month. So yeah, again, thank you all for coming. I hope to see you next month, and I hope to see you on Zulip in between. So yeah.
Great.
Have a good evening.
Just some last points. Yeah. Please remember to follow Formal Ferris on Twitter, because you will see updates on future events, and also continue the discourse in the Zulip as well. So at Formal Ferris, for those of you that are on Twitter, most of the discourse will happen in the Zulip. So please, please, please continue the positive momentum that started from this in there. And it's very important that this becomes a holistic effort from everyone. So if you have a topic that you want to present, this is your opportunity to do so. Please speak with Xavier, who's going to be leading the community, or Bas, and they'll be able to work out a schedule for you to, excuse me, share what you have going on. This meeting is also recorded as an archive and will be shared on YouTube channels. So if you know someone who would like to have been here and missed it, please refer them to the YouTube channels that we will share in due course. And again, thank you all very much for coming. Xavier, do you want to have the last word? Just to say a big thank you to our speaker and everyone else.